Dear colleagues, dear guests, welcome to the 20th IFS Seminar. Today it is our pleasure to present Murat Saglam from University of Cologne. Murat works in symplectic geometry, and I had the pleasure of sharing our PhD institution with him back more than 10 years ago in Leipzig. Yeah, Murat will tell us a little bit about some aspects of low-dimensional symplectic geometry, contact geometry, and we hope to learn much today. So, Murat, please choose for yourself whether you want to be interrupted during the talk or you want people to keep their questions to the end.
I mean, just you interrupt me as much as you can.
All right. So, and then you have roughly 1 hour for the seminar, and then some Q&A.
Okay, very good. Okay.
Thank you. You have your time, please.
Okay, so yeah, thank you very much for the invitation, for giving me this opportunity to talk about this this form of an audience. So I guess it will be a nice experience for all of us. Yeah, so I want to talk about integrable Reeb flows. And I will tell you what I mean by integrable, what I mean by Reeb flows. But an integrable here is really in the sense of integrable systems and Hamiltonian mechanics. And then a Reeb flow is essentially an Hamiltonian flow, but which is seen as its own sake, is in its own, let's say, mathematical context. So I think it would be a familiar object at the end. Okay, so I will start recalling basic stuff. Just for the sake of recalling, I guess all of you are quite familiar with what I will say in the following 10 minutes maybe. So main object here is a symplectic manifold. So this is a 2n-dimensional manifold with a differential 2 form, which is supposed to be closed, and then its end power, so as you take the end wedge product itself, you get a non-vanishing top form. So it gives you a volume form. And then equivalently, this means this 2 form seen as a map at E for every point P. Now you can see this as a map from the tangent space to the cotangent space. Yeah, you pick a vector, you plug it in omega, it still waits to eat another vector and then hooks up a number. And this non-degenerate, so-called non-degeneracy condition says that this omega is an isomorphism at every point. So that's the typical or the standard example is an Euclidean space of 2n dimensions. Let's say with these coordinates q1 up to qn and p1 up to pn, then this 2 form omega is a standard standard symplectic form is the typical example. And then this structure, unlike the Riemannian metric, for instance, it doesn't have any local invariant. So we have a theorem due to Darboux, which says that given any symplectic manifold of this sort, around any point there is a neighborhood, and there are these coordinates such that your symplectic form is precisely this one. So locally, we have sort of a flat structure, so it doesn't really have any local invariants. And then the next example is maybe it's more familiar to you. So for instance, what you can do, you can take a manifold of dimension n and look at its cotangent bundle. So you take a configuration space of n dimensions, and then you look at the phase space, and then you have the canonical symplectic form given by this expression here. Qi's are the position coordinates and pi's are the momentum coordinates. And then this is as a non-compact object. So, and then as you may see, because of this condition and this condition, if your manifold, if your manifold is closed, your symplectic form cannot be exact. But then here we have an non-compact manifold, and in fact, this canonical symplectic form is exact. It is the differential of the Lugel form. This is a 1 form. It's a canonical 1 form given by this expression in local coordinates. And then here we have a little bit of a structure that kind of will be relevant also later. For instance, this canonical 1 form, actually this is a 1 form, you have your non-degenerate 2 form, via this identity, then this defines a unique vector field. So you plug there, define this vector field y, so that when you plug this y into omega, then you precisely recover the canonical one form. And then here, this omega is really this, so to say, the radial vector field. Yeah, so at every cotangent fiber, it points out to the radial direction, and then it has this property that this is a symplectic vector field. So, yeah, so the Lie derivative of the symplectic form along this y is again the symplectic form is in part. If you integrate this equation, this tells you this actually expands, so to say, the symplectic area of objects as you follow the flow of the Liouville vector field. So we have these two standard examples, and then maybe a compact example would be, standard compact example would be the complex projective space. So another example would be, again, let's say a closed surface of genus G, and then you take an area form. It's an area form, which means it's non-degenerate, and it's obviously closed because it's a two form on a two manifold. And this would be an example. And then also you could consider the two torus. So basically, you can look at this example of R2D2N and then look at your two form, and then you realize that it's really invariant if you just do the shifts in any coordinate, which means that it induces, again, a symplectic form on torus. Okay, so now on a symplectic manifold, so you can always think this symplectic manifold to be the phase space. Yeah, so you can forget about the general notion of a general symplectic manifold, because for the rest of the talk, it's really the symplectic manifolds that we are looking at will be sort of phase spaces. So on. Okay, but in general, so given a symplectic manifold, given a smooth function on this, a Hamiltonian, then you have the differential of the Hamiltonian. This is a one form, and then this equation here defines you a vector field, which is the Hamiltonian vector field, as you all know. And then, for instance, if you have a regular level set of this Hamiltonian, let's say a regular energy level, which is a nice manifold, then you have a nice vector field, which is in fact tangent to this energy level and defines a flow, defines the Hamiltonian flow via the usual Hamiltonian equation. Yeah, so for example, one standard example might be, you take again, as your symplectic manifold, you take the phase space, you take the canonical symplectic form, and then you look at the kinetic energy Hamiltonian. Yeah, and then you have a energy level, a regular energy level, and then you have the Hamiltonian flow, which would give you a reparameterization of the geodesic flow. Right. Okay, now we have symplectic manifolds, we have Hamiltonians, and then now I want to just fix what I mean by a completely integrable Hamiltonian flow or a Hamiltonian system. So I start with my symplectic manifolds. I have my Hamiltonian. I say this will be completely integrable. If the following holds, so basically, in terms of physics, I just need enough integrals of the motion. That's what it means. More precisely, I want to find another n-1 Hamiltonians, so the F2 up to Fn. And then so for the convenience, I define F1 to be my Hamiltonian H that I start with. So I have n Hamiltonians with the following properties, as you see. So the Hamiltonian vector fields are complete, since I'm not assuming any compactness for the moment. And then the other condition is that you want these Hamiltonian mutually Poisson commute. So you define the Poisson bracket of two smooth functions via just plugging in the Hamiltonian vector fields in your symplectic form. And then the condition here is that you want this bracket to vanish. And then the outcome of this condition is the following. One can easily see what a computation is, that if you take any two functions and take their Poisson bracket, this is again a function, and this defines another Hamiltonian vector field. The Hamiltonian vector field that is defined will be precisely the Lie bracket of the Hamiltonian vector field. So once you assume this Poisson commutativity, then this tells you that the Hamiltonian vector fields also commute. So their flows, they commute. So the other condition that you want is that the differentials, or like if you want the Hamiltonian vector fields to be linearly independent as much as possible. But of course, for a compact symplectic manifold, this will definitely fail, yeah, because on a compact manifold, you have your smooth function, which will have critical points. At certain places, the Hamiltonian vector field or differentials will vanish. So this will not hold, cannot hold on the whole manifold. But then, for instance, in the compact case, you say, this is also the thing, there are different notions of integrability. So some people like to assume that these one forms or the vector fields will be linearly independent on an open dense subset. Some people say, accept a measure zero set. This is Liouville integrable, for instance, in the literature, but we will assume something more. So we will kind of assume more structure on this critical set, so to say, to be able to say something about the topology of the underlying energy level. Okay, and then another thing to remind is the famous Arnold-Liouville theorem. So once you have such a complete integrable system, then you can look at this this map from your symplectic manifold to Rn where the components are given by the Hamiltonians. And if you take a regular level, then the pre-image of the regular level will be a Lagrangian torus. So it will be it's a regular level, which means it will be a manifold of dimension half. And then because of this commutativity conditions, you know that your vector Hamiltonian vector fields are all tangent to this half-dimensional object, and then they Poisson commute. This already tells you that this half-dimensional object will be Lagrangian, and then you have to argue that this actually just following the flow lines of these vector fields, this n non-vanishing vector fields, you can actually parameterize this level set, and it becomes a torus. And moreover, then there will be a neighborhood of this Lagrangian torus, which will look like, yeah, so it's like a trivial neighborhood of the torus here. So a torus, and then you have a ball of dimension n, a small ball. Moreover, you have on the space, you have these coordinates, which are called the action angle coordinates, such that your symplectic form really looks like the standard one. So here, these coordinates, θ1 to θn, is basically they parameterize the flow lines of the Hamiltonian vector fields, and then R1 to Rn gives you the corresponding nearby values of your integrals. Now, so the Hamiltonian flow of each Hamiltonian on this regular level will be a linear flow. So it's a very nice structure theorem, which kind of enables you to completely understand what is going on with this Hamiltonian system near a regular level set. And then, of course, when you're close to a critical set, things can get wild. But nevertheless, you have a very good understanding, at least around the regular levels. Okay, so these are the basic objects. Here we have symplectic manifolds, we have Hamiltonians, integrable systems. Collection of Hamiltonians which form a nice integrable system. Now, so what is a contact manifold then? I mean, how this thing comes out. So I kind of want to motivate the notion of a contact manifold. So let's say we look at again the phase space. So we pick a Hamiltonian. Let's say we have a nice regular level set, which I call M. And of course, this is codimension 1. So this is now an odd dimensional manifold. And then, as I said, we have this on the phase space, we have this Liouville vector field, this radial vector field. So let's assume for the moment that this radial vector field is transverse to this energy level. Yeah, so like and it's a fiber-wise phenomenon. Yeah, so at each cotangent fiber, I have the intersection of the cotangent fiber with my energy level. It looks something like this, and then I have my radial Liouville vector field, and I want this to be always transverse. Yeah, transverse means in this case not tangent. Yeah, and then what you can see is then the following. Now you can take the Liouville form, so this primitive of your symplectic form, and then you restrict it to the tangent space of this regular energy level. Yeah, then I call this by alpha. This is a nice one form. And this transversality condition here tells you that in turn, if you take alpha, this is a 1 form. Then you take d alpha as a 2 form. You raise d alpha to the power n minus 1. You get a 2n minus 2 form, and then you wedge it with your alpha, you get a top form on m. Now, it turns out that this transversality provides you the condition that this top form will be non-vanishing. It will be a volume form. So then if you're familiar a bit about the theory of distributions and foliations, this condition of sort of non-degeneracy that appear here tells you that the following. If I look at this 1 form, and look at its kernel. Yeah, so this is a 1 form, it's nowhere vanishing. So its kernel will be a 2n minus 2-dimensional hyperplane at each tangent space. Yeah. Now you may ask this question whether I can integrate these hyperplanes, whether I can kind of so find submanifolds which would be tangent, let's say, locally to this distribution. But in this condition here, this non-degeneracy tells you the following. This hyperplane distribution is something very ugly. So it's actually something which is maximally non-integrable. In the following sense, so you cannot integrate this, so you cannot really find a 2n minus 2-dimensional submanifold of M, which would be always tangent. This is something you cannot do, but you cannot even do anything above any like you cannot really partially integrate above the dimension n minus 1. Yeah, so which means so let's say Q is 3-dimensional, phase space is 6-dimensional, my regular level is 5-dimensional, my plane distribution is 4-dimensional. This tells you, okay, so you cannot find really a 4-dimensional submanifold, which is tangent. You cannot find a 3-dimensional submanifold, which is tangent. The best you can hope is to find something 2-dimensional, which stays tangent. Yeah, this is non-integrable in the worst possible sense. And this itself, having such a distribution, such a maximally non-integrable distribution, so it becomes mathematically interesting. And then okay, you say, okay, then let me define a new structure on an odd-dimensional manifold. Yeah, now we forget, you keep in mind this example of the regular energy level, but now an odd-dimensional manifold is a dimensional 2n minus 1. I would say a 1 form alpha is a contact form if it satisfies this non-degeneracy condition that I saw in the example. And then the kernel of this alpha, so this alpha again by this condition is non-singular, so its kernel is of dimension 2n minus 2. It's a hyperplane distribution, and then I call this hyperplane distribution a contact structure. So this is a sub-bundle. So you have my manifold M, I have its tangent bundle. So Xi itself is a sub-bundle of codimension 1. So my tangent bundle actually splits into 2 sub-bundles. I have this Xi, this hyperplane field, and then I have this complementary one direction, and then I kind of parameterize this complementary one direction in the following way. I pick a vector field R, which always points transverse to Xi, and then I fix it in such a way that if I plug this R into my 1 form alpha, I will get constantly 1, and this R really will lie in the kernel of the alpha, which actually tells you that this R is really transverse to Xi. So this is the terminology. So this is now, such an alpha will be a contact form, and its kernel will be called a contact structure, and then this vector field that I define here will be called the Reeb vector field of the contact form alpha. So so we have this nice example of a type of an example of a hypersurface, an energy hypersurface, which comes up with this interesting non-integrability. This is a non-integrable hyperplane field, and then now we're kind of making this, turning this into a definition. So the examples again. So if you go back to our example, which was motivating the definition of a contact form. So so this hypersurface, this regular energy surface, will be my contact manifold, and then my Reeb vector field in this case will be up to reparametrization of the Hamiltonian vector. So that's why, so you want. You can simply forget contacts, or maybe not. But for the moment, you can think this as always. We're taking the regular energy level for an autonomous Hamiltonian, and then the vector field we are looking at is the Hamiltonian vector field. But then, of course, as it is this typical example. So, as in the symplectic case, so the typical standard example you take is this odd-dimensional Euclidean space. Let's say with coordinates x1 up to xn and y1 up to x1 up to xn minus 1, y1 up to yn minus 1, and then the coordinate z. And then you define the standard contact form with this equation. And then this defines actually a contact form. So it satisfies this non-degeneracy condition. And then here's a picture from Wikipedia. So this would be the picture of this hyperplane distribution in case of R3. Yeah, so you can see, maybe we spend a bit of a time on this picture. Yeah, so if you look at this one form, yeah, so we have this plane field is the kernel of this one form at every point. Yeah, so for y equals 0, you see, I mean, on this line, or maybe, oh no, sorry, on this line, of course, this makes more sense. So on this line, my one form is simply dz, so its kernel is just the horizontal plane. Yeah, and then as you see, yeah, you can actually integrate, and you can find the one-dimensional submanifold of R3, right, a curve which stays always tangent, which is still fine. Yeah. So in this case, the hyperplane field is two-dimensional, so you cannot integrate the plane field, so you cannot find the local surface, which will be tangent, but still you can find this one-dimensional submanifold, which will stay tangent. And such things are called Legendrian submanifolds, by the way. But then you see, maybe from this picture, one gets the gets the impression why you cannot integrate this plane field. Yeah? So if you, for instance, if you fix this line, x equals 0, and then look at what happens to the plane field. So it's like center, it's really horizontal. And then as you go to one direction, it starts tilting. And then as you go to infinity, it will come close to be vertical. Yeah? And if you go the other direction, the same thing happens. Yeah? So you start horizontal, and then you start tilting, and then eventually at infinity, it will become vertical. And then the same behavior happens on the other direction. So this somehow may give you some feeling why this plane field cannot be integrated, maybe. And then, as in the symplectic case, we have a Darboux theorem for the contact manifolds, which tells you that given a contact manifold and given a point, and there's a neighborhood, and then you have these coordinates of this form such that your contact structure, the hyperplane field, is given by the kernel of this one form. So it's not really saying if you fix a contact form, then there's a for every point there's a neighborhood that your contact form will be precisely this. This you cannot say, but the kernel is always given by the kernel of this one form. Yeah, so essentially it tells you that the structure here is not the one form, but the plane distribution or the hyperplane distribution in general. So another example is again R3. Now I'm looking at I'm taking the cylindrical coordinates in R3. Yeah, so I have my z coordinate on the xy plane. I have my angle phi and then my radius r. And then I define this one form, cosine r dz, sine r d phi. And then one can easily check that if you take, so if you take alpha, which d alpha, this is nowhere vanishing. And then if you look at the picture of the kernel, this is pretty much what you see. Yeah, so at each radial direction, for instance here, so again, at the center, the plane is horizontal, then it starts tilting, and then here at this point, when r is a period of cosine sine, then it again becomes horizontal, and then it keeps turning. Yeah, as you move in the radial direction, it periodically keeps turning, and then the same behavior repeats itself in this direction. This is another example. But of course, as in the case of any mathematical structure, you have the notion of an equivalence. So, Riemannian metric, for instance, would be an isometry. for instance, for the object of the contact structure, it would be a diffeomorphism which would map one contact structure to another one through its differential. And then, of course, you may ask, okay, I have now the same space R3, and then I have two examples of such plane fields. One is this one, the other one is this one. And then a priori, you don't really know whether they are diffeomorphic. Yeah. So usually what you ask to yourself, yeah, whether I can classify my my structure up to equivalence. So now I'll go to the direction, what's going on with the classification. But before going into that, I have to come up with to give a definition of something. So if you look at this picture, so this is R3, and then I have this nice disk in R3 on XY plane. And then this disk has the following property. So this is a two-dimensional submanifold, right? So, and then it can never be tangent to my hyperplane field or an open subset, because this would mean that I can integrate my plane field. But then this has this property that on the boundary, at every point on the boundary, actually, the tangent space of the disk coincides with the tangent space of the coincides with the plane field. Yeah, so you see, at every point on the boundary, my contact plane is horizontal, but this is precisely the tangent space of the disk at the boundary point. Yeah, and this is this weird property, and such a thing is called an over-twisted disk. And then you don't ask me why it is called over-twisted. Yeah, so it's I don't know why exactly, but this is an object which pops up for certain contact structures and which does not pop up for certain other contact structures. For instance, for this picture, you may think that such a disk does not exist. Of course, your disk doesn't have to be a nice flat disk, you know, it can be curved and banded in any way. But then if you look at this plane distribution, it seems to be unlikely. And then it turned out that actually the existence of such disks provides you an interesting dichotomy. So now I'm thinking, from this point on, I'm only thinking of three-dimensional contact structures. So my contact planes are really planes. My manifold is three-dimensional. And then I make this following definition. I would say a contact structure is over-twisted if there is an over-twisted disk. Something precisely like this. I mean, not precisely, because this over-twisted disk is very nice in the sense that, I mean, in the inside, you could have points where the tangent space of the disk is still tangent to the contact distribution. But in this nice picture, this only happens in this point. And then everywhere else, the tangent plane of the disk intersects the contact plane transversely. Yeah. But then the defining condition is precisely this. So at every boundary point, I want my tangent plane of the disk to be the same as the contact plane. And then I say a contact structure is over-twisted if there is some over-twisted disk somewhere of some sort. And then I say it is tight if it is not over-twisted.
Sorry for interrupting. So yeah. Locally, they are all same because of the Abu theorem.
Yeah, true.
But globally, because this, I mean, you brought the example of a periodic kind of field, and this period is a finite distance, so that's why it's really a global phenomenon. You may or may not have that condition. Right?
Exactly. I mean, from the Abu theorem, you can kind of probably easily argue. I mean, it shouldn't be too hard to see in this model. You don't have the disk. Yeah, somehow this suggests to you that this disk does not exist locally, but it's rather, although it's a disk, you know, it's a compact submanifold. And so usually a disk is something that you can move everywhere you want, but this is supposed to be something global.
So in higher dimensions, do other kinds of objects appear, or are they just all like simply connected like a disk?
No. So in this, the dichotomy you have in every dimension. I mean, for some time it wasn't really completely clear what would be the thing which would correspond to an over-twisted disk.
Yeah.
So there was one suggestion, another one, and then now pretty much we have a nice notion of over-twistedness in every dimension. I mean, of course, it sounds weird. I mean, why you would define such a property? And then I guess if one makes sense of this definition, if one knows the proof of a certain classification result of the contact, because these objects they pop up when they exist somehow. They enable you to deform one contact structure into another one in a certain way. But this I will not go into. But nevertheless, we have this God-given dichotomy. Yeah? So it's over-twisted structures, we have the tight ones. And then obviously this is a dichotomy in the sense that it respects the equivalence. So yeah, so equivalence you can think, as I said, in terms of two contact structures being diffeomorphic. But there's also another way of defining an equivalence. So for instance, you can say two contacts, you can look at the isotopy classes of contact structures. So let's say one contact structure, one plane distribution, you have another one, and then there's an isotopy. There's like a smooth one parameter family of contact distributions which connect one to the other. And then a priori, such an isotopy doesn't have to be realized by an ambient isotopy, but in the case of the contact distributions, it is. So there's a very straightforward observation due to Moser, which is called the Moser trick in symplectic geometry. It's extremely useful. And using this, you show that if you can deform one contact structure to another one through contact structures smoothly, then this deformation you can realize by an isotopy of the whole manifold. In particular, if two contact structures are isotopic, then they will be also diffeomorphic. Yeah. And that's why if you have two isotopic contact structures, if one is over-twisted, that the other one has to be. Yeah, because then you have this over-twisted disk, then you have a diffeomorphism which sends this one to an over-twisted disk. And then now comes the important theorem, which kind of somehow the reason that we have such a dichotomy. So now you have your manifold, you have the tangent bundle, you have a plane field. Yeah. And of course, you can first of all ask the following, you can get the homotopy classes of plane fields in your manifold. Yeah. So you forget the contact condition. And then you may ask, okay, how many homotopy classes of plane fields do I have in the first place? Yeah, because essentially the idea is, so the aim is to understand the isotopy classes of contact structures, but then you first ask, okay, let me see whether I can homotope them as plane fields. Yeah. Maybe I deform one to the other one, but along the way, I don't care whether I get a contact distribution all the time. And then there comes this very important theorem of Eliashberg, which says, if you have a closed tree manifold, then if you fix a homotopy class of plane fields, then within this homotopy class, there's a unique over-twisted contact structure. Unique here is up to isotopy. Meaning that if you give me a homotopy class of plane fields, I know in this homotopy class of plane fields, there's a contact structure which is over-twisted. And if I have another one in the same homotopy class, which is also over-twisted, then I can isotope one to the other. And this is the place where during this existence of this isotopy, this is where this over-twisted disk becomes relevant. Okay, let me give some more examples. So for instance, so far the only contact manifold that I told you is R3 or R to the 2n-1. Another one is our standard S3. Now you see this S3 is really like the unit ball in R4. And then on R4, you have your canonical symplectic form, canonical Liouville form, and then you just restrict this Liouville form to the tangent space of S3. And this defines a contact structure, again, because in the same spirit that you have the Liouville vector field, which is always transferred to the sphere. Yeah. So this is so-called the standard contact structure, contact form, and then its kernel is said to be the standard contact structure on S3. And then you have the Reeb vector field, as I said, the complementary thing. And then this Reeb vector field is really what it gives is the flow lines gives you the Hopf vibration. So you have the vibration of S3 by circles. Yeah, maybe this is so you have this map from S3 to CP1. We just see this S3 as a subset of C2 with two complex coordinates, and then you send each point to its corresponding point in CP1. Yeah, and then above every point on CP1, you have precisely one circle. This gives you a circle fibration of S3, and then in this case, these circle fibers are really the closed orbits of the Reeb flow. So, and then we have another important theorem, which tells you, for instance, on S3, this contact structure that we have is the unique tight contact structure. Which means if you have any other tight contact structures, contact structure on S3, then this has to be isotopic to the standard one. Yeah, so the situation here, let's say on S3 is like use the previous theorem for in every homotopy class of a plane fields, you have a unique or twisted contact structure, and then there's only one tight contact structure. So this gives you the full classification, for instance, of the contact structure on S3. Another example, which can maybe because of the names of the objects and so on might be familiar or maybe interesting. It's kind of a generalization of the previous example in a way. So let's say I have a principal circle bundle. Yeah, and then this is my base space. Now on this principal circle bundle, let's say comes up with a connection one form. And then this connection one form provides me a curvature form, which is a 2 form on this base manifold. So if this curvature 2 form is actually a symplectic form here, then the connection 1 form is actually a contact form. And this, yeah, so in this situation, what we call this object is a pre-quantization. And then that's why I put this alpha PQ, so this PQ in the subscript. So this is the pre-quantization contact form. And then one can, so for instance, see that actually this contact form is also tight. This contact structure that comes out from here is also tight. But using this example, maybe you can combine these 2 types of examples. So we have this contact manifold structure on a principal circle bundle. And then we have the example of the contact manifold as the regular hypersurfaces, energy hypersurface transfer to the Liouville field. Now you can combine these 2 things in one setup. So let's say I have a surface. I take the cotangent bundle. I take my kinetic energy Hamiltonian. I take a regular level, let's say of a level of 1. So I'm taking the set of unit cotangent vectors. This is what I'm trying to say here. This is a unit cotangent bundle of sigma. Now, this guy, as being this nice regular energy hypersurface, it has this contact structure where I just take the Liouville vector field and restrict, where the Reeb flow becomes the geodesic flow. So this defines one contact form, which is a kernel. So the contact structure that I'm considering. But on the other hand, this object is a principal circle bundle over its base. Yeah, because above each point, you have the set of unit cotangent vectors, which forms a circle. So this falls in the category of this pre-quantizations. This gives you, for instance, to me, another contact form, which would define another plane distribution. So for instance, these 2 plane distributions, they are both tight, but they are not isotopic. Yeah, so this phenomenon that happened for S3, for instance, the fact that there was a unique tight one, here you don't have it. You have more than one tight contact structure. All right, so,
Can I ask a few questions?
Yes.
Sorry,
Yes.
I'm afraid that, so first I have to go back
Yeah.
to the very definition of a twisted disk. So maybe I think you said it, but I missed it. So the boundary, so the distribution has to be tangent to the boundary, right? But and not inside, but there is a point inside in this example.
So what is happening here is the following.
In the center.
So the condition is this: you take any point on the boundary here. The condition is, so on this point, okay, you have your contact plane, and then of course you can make sense of the tangent space of the disk at that point. Although it's on the boundary, yeah, the whole tangent space makes sense.
Right. This part I understood. What I didn't understand is what you require inside.
The requirements is precisely for every point you want the contact plane to be precisely the tangent plane, but for every point on the boundary. So this happens only on this one-dimensional piece.
No, but is there a request also on what happens in the inside or
No, not really. No.
No. Okay. Sorry. Okay.
Not at all. No, it's just what happens in this picture inside is like the nicest thing that you can have inside, so to say. But the behavior inside might be wild, but then there's also this, what you can argue it is a certain way of perturbing an over-twisted disk so that you would always achieve, let's say, a picture which is quite close to what you see here. Yeah,
I see, but I kind of go full by this example into that into thinking that perhaps generically inside you did there should be some transversality condition.
So the thing is the following. Definitely there will be some other points inside where the tangency will happen.
As this example illustrates.
Yeah. So, and then you may have many of them. Yeah. And then this transverse intersections. Yeah. So now here we have this transverse intersections that we can integrate, and then they will provide us the radial lines, which look quite nice. But in principle, you may have many sort of say singularities, then transverse intersections connecting them, foliation may be wild. But the point is, you can always perturb such an over-twisted disk in such a way that you get rid of all the nasty behavior.
Okay.
Yeah, that's the thing. But then
none of this is
doesn't really matter. The only condition is really about what's going on in the boundary.
Okay. Thanks. Sorry,
no problem.
I think I misinterpreted something you said at some point. That,
okay. Yeah, maybe I.
No. Okay. So the next question. So about this. So I missed the. So if you gave So the this is the on S3. You said that there's only one example. So the Hopf vibration provides the only tight contact structure. What about the twisted ones?
Yeah, for the ortho-twisted ones, we have this general theorem which applies any closed tree manifold. Which means on S3, for instance, we have to ask the following question. So how many?
So this is always okay. So this is a tree here. This number is a tree.
Yeah, this is 3. Yeah, this is a closed tree.
Okay, sorry.
So in the case of S3, so maybe I should say this. So in the case of S3, for instance, this theorem tells you the following. Okay, so if you first ask the question, how many homotopy classes of plane fields do I have on S3? Okay, so how do I describe the homotopy class of plane fields? Yeah, so if you have a plane field, yeah, then you can pick like a complementary vector, which is unit to this plane at every point. Sort of a Gauss map. So this tells you that any plane field is associated to a map from S3 to S2. Yeah, because the tangent space of a tree manifold, yes, it's orientable, it's parallelizable. Yes, and you can, the tangent space is trivial, which means any plane distribution can be described by a function from S3 to S2. Yeah? This function will give you at every point a normal vector to the plane. Yeah? Well, then two plane fields will be homotopic if and only if these functions are homotopic.
Okay.
So then the plane fields, the homotopy class of plane fields are parameterized precisely by the homotopy class of maps from S3 to S2, which is precisely pi2 of S3, the second homotopy group, which is isomorphic to Z. And then this theorem tells you for any number in Z, you have a homotopy class of plane fields, and then in this homotopy class of plane fields, there's a unique over-twisted contact structure, which means on S3, I have Z many non-isotopic over-twisted contact structures, and then I have one tight structure, which is not isotopic to these Z many objects, and that's all. That's all I have.
Fantastic. Okay.
Yeah, you're welcome.
Thanks.
Oh, that's very good. That's very good. Right. So again,
sorry, can you remind the definition of the plane field?
I mean, plane field is just the following. So you're in a tree manifold, you have the tangent bound. At every point, you have a 3-dimensional tangent space. So a plane field is a smooth distribution of 2-dimensional planes at every tangent space. Okay. Yeah. So, or if you want, a better definition would be you have a one form, a differential one form, which is non-zero. Yeah, and then at every point, it has a tangent space. This one form is a linear map. from the tangent space to R, and then it has a two-dimensional kernel, and this is your plane.
Okay.
The form is smooth, the distribution is smooth. Yeah, so every contact distribution in dimension 3 is a plane distribution, but I mean, you could have a plane distribution where you can integrate, you know, so you can just have sub-manifolds and stuff. That would be tangent to a given distribution. But then, yeah, so this one, the contact distribution is the one which is really non-integrable one. Unintegrable ones. Okay, now I want to talk about the integrable Reeb flows. But I don't want to really talk about, I don't want to see them as, as energy hypersurfaces and so on, which is something that I can always do. But I just want to have a definition of integrability, let's say of a three-dimensional contact manifold, the integrability of a Reeb flow. So now you can think this three-dimensional manifold as a regular energy level in dimension 4, which means you're basically thinking this four-dimensional spherical manifold. And then this Reeb vector field is a Hamiltonian vector field of one Hamiltonian. Then you need another integral to get the maximum number. So in this spread, you say, I say it's integrable if I can find a function on my energy surface such that its differential vanishes on R, which means along the flow lines of the Reeb vector field, my function is constant. Yeah, this is precisely this Poisson commuting condition, if you want. And now I had the other condition about linear independence. Now this condition is replaced by asking this f to be a Morse-Bott function. So you know what, I guess, I don't know whether you know what a Morse function is. Or should I remind what a Morse function is? Maybe I should. Yeah, so what's a Morse function? So you have this is a function on a manifold such that the critical points are all isolated. And then at every critical point, if you look at the Hessian of this function, the Hessian is non-degenerate, which means essentially that your function looks like in suitable coordinates, it really looks like, I don't know, let's say in dimension 3, depending on the type of the critical point, maybe it will look like 1 squared x squared y squared z squared, or minus of this, where you would have, let's say, a maxima, or minima, or maybe even you have this changing signs. You maybe have this kind of a saddle behavior, or maybe this kind of a saddle behavior, and so on. Now, so it's a function. This in the case of a compact manifold, then this would mean that you have finite many critical points, and around this critical points are isolated, and around them you have this nice second-order behavior. So either you have a local maximum or local minimum, or you have certain types of saddles.
You could say the second-order Taylor expansion is nowhere trivial.
Exactly. Yeah, this would be a nice way of saying it. Okay, what is Morse-Bott? Well, Morse-Bott is a bit more than Morse. Now, you allow your critical set to be not isolated points, but submanifolds, which would mean that you could have a critical circle, critical surface, but nevertheless, in the complementary direction to this critical set, you again ask the same non-degeneracy condition about the Hessian. Okay, why this is relevant? I mean, because this is, I mean, remembering in the definition of completely integrable system, we wanted this set of integrals to be linearly independent on a set which is as big as possible. Yeah. And here, this is the place where the linear independence fails in that sense is precisely the set of critical points of f. Now we want this critical set, the critical points to have a nice behavior, or like this f, the critical set itself should be nice, and then the f itself, the integral, should be also nice near the critical set. Because this is somehow you can extract some structure on your manifold. So this is also something that I will skip. Why? I mean, so this is why this is somehow equivalent to the previous sense of integrability. But let me just go to some examples. So, for instance, again, the standard example that we had this S3, where we had the standard contact form, which was defining the standard contact structure, which was the unique tight one. And then we had this Reeb flow giving us a circle bundle structure, the Hopf vibration. So for instance, in this case, there's a very nice integrable Reeb flow, because basically on this quotient space, on the orbit space, you can pick a Morse function. Yeah, on CP1, which is S2, you take some Morse function with isolated critical points and stuff. So there may be some Morse function which will make S2 look like this. Yeah, but then you can lift this function to S3. You just define it to be constant along the S1 fibers. Yeah, and then this object is really is a Morse-Bott function. And then this is a nice Morse-Bott integral for the Reeb flow. Or more generally, if you have this situation of a pre-quantization bundle, so there's a circle bundle over a symplectic manifold, and again you can pick your integral on the orbit space, and then you pull it back to your contact manifold as in such a way that it stays constant on every Reeb orbit, and then this would provide you the integral. But let me skip this for the moment, because I kind of have to save time. So a couple of things one can easily observe. If you have such an integral, so the critical set is consists of submanifolds. If the contact manifold is compact, which is always something we assume, then if these critical sets components are one-dimensional, then they have to be closed orbits. Because if I have a point where F is critical, if I take the flow line of the vector field, every point on the flow line will be critical. Yeah, and then due to the compactness, this has to be a closed submanifold, and then this will be a closed orbit. Or it can be two-dimensional. It will be then a surface. But then if it is a surface, it can be only T2 or a Klein bottom. And then don't ask me. I mean, I can tell you why, because these are only two surfaces which would admit a non-vanishing vector field. And so the critical set, the Reeb vector field is always tangent to it. It's non-vanishing. Then the Euler characteristic has to be 0, and these are only possible surfaces that you can get. And then because of this Morse-Bott assumption, you have nice coordinates near the critical set. Yeah. And then if you look at the regular levels of this function, again, the regular levels will be 2 tori, as we saw in the case of integrable Hamiltonian systems. And then nearby, you would have nice action angle coordinates. Okay, now comes a theorem which tells you the following. If you have such a tree manifold, which would admit an integrable Reeb flow, a closed tree manifold, then this tree manifold has to be a graph manifold. Okay, what is a graph manifold? Let me try to tell you what's a graph manifold. A graph manifold is the following. So you have these two types of building blocks. So you have a solid torus, and then you have a solid torus where you remove two small solid tori from inside. So this is my building block of type A. This is type B. So these are all three manifolds, both of them, three manifolds with boundary. The boundary here is just the two torus. And then the boundary here is just, we have one two torus outside and two tori inside. The graph manifold is something where you can take a bunch of these building blocks and then you glue them together along their boundaries. Yeah, so each such building block has a boundary component which is a torus, and then you can glue, for instance, this guy to the other guy along their boundary using a map, using the diffeomorphism of T2. Yeah, so depending on how you glue, of course, you create topology. But the graph manifold is something that you can obtain in this fashion. And then somehow this theorem kind of makes sense, I hope. At least it is believable. Yeah, because what do we have? So we have this, when you have this integrable Reeb flow, and then we can kind of decompose our manifold into pieces. Yeah, around regular levels of my function, I have a T2, and then like a thick neighborhood of T2. This is my piece. And then when I come close to the critical set, this is pretty much the picture that I will see. For instance, here I would have, this would be like the core circle will be like a critical circle where my integral is really like, so this R is this radial coordinate of the disk, maybe my Morse-Bott function looks like R squared, where I'm having this minimal, this is this critical set, which is a circle, which gives me a local minima, or maybe a local maxima. And then this is the situation where you would see around a saddle, so to say. Yeah, so my function f, yeah, maybe it's a Morse-Bott function on a 3 manifold. Let's say the critical set consists of just circles, no surface and anything fancy. Then at every critical circle, you have 2-dimensional transverse directions. Yeah, and then the Hessian will be a 2x2 matrix. If it is positive definite or negative definite, then you are either in a local maxima or minima. And this is pretty much how the local picture would look like. And then if the signature of this guy is -1, yeah, then really like it's like a saddle. It's kind of like a 2-dimensional saddle where you're fibering the bob you're fibering with circles. These are kind of pretty much what can happen topologically, and then this tells you can kind of decompose your manifold into such pieces. And then the converse is also true. If you have such a graph manifold, I mean, these pieces, you can actually construct, define contact forms on each piece such that they actually glue together in a nice way and then give you some contact form globally, which is a vector field, which is integrable. And then the integral really comes from these pieces of the integral comes from Morse functions on these surfaces. I don't know if this makes any sense. I hope it, maybe, yeah.
Building block of type B by itself doesn't look like a circle bundle, does it? Yeah.
I mean, this is it's a circle bundle in the following sense. Yeah, so there's all these vertical lines, they are circles.
Okay.
Yeah,
yeah.
so this is this type
In that
is really
sense,
like
yeah.
this pretzel times S1.
Yeah,
This
okay.
is really
yeah.
disk times S1. Yeah,
Nice.
this is what I mean.
Yeah, okay.
Okay, now comes, so this is classical. So this is really was known to the people who were doing Hamiltonian systems. Yeah, there's this book of Bolsinov and Fomenko, a thick one. Maybe you
Ancient Greeks, right?
yeah. So it's a thick book on integrable systems. Not easy to read, but it has a lot of stuff. So this classification was very well known. But then that comes kind of out of this, there comes this mathematical question. So let me just at least state the question and motivate a bit, and then I will stop. If you give me another 5 minutes, maybe. So now you ask the following question: is someone doing contact topology? You say, okay, now given a graph manifold, now I know that there is some integrable Reeb vector field on this guy. But then again, this graph manifolds have possibly many contact structures. Now the question is whether, given a contact structure on this graph manifold, I can find a contact form which defines this contact structure. Yeah, this was something that I didn't mention, but I should have. So if you fix your contact structure, of course, you can find many contact forms which would define this. Yeah, if you have kernel of alpha 1 equal to kernel of alpha 2, then this is if and only if alpha 1 is just a function times alpha 2, or this function is non-zero, let's say positive. But then if you look at the vector fields associated to these two forms, they may be extremely different. So their dynamics can be a priori very different. And then you say, okay, maybe if, so topologically, you know what is the topological abstraction for the existence of such a flow. But then you ask if there's a contact topological abstraction. Yeah, so if I have, if for every contact structure, for instance, can I find such a thing? And then the answer is no. That's why this is an interesting question. And then the answer is no because of the following fact. So this is something that I kind of want to discuss, but I will just say it. So given a flow, you can associate a quantity to this flow, which is called the topological entropy of the flow. So it basically measures how complicated the flow is. Let me just say this. And then the theorem is the following. If you have an integrable Reeb flow, then the entropy of this flow has to be 0. But then, for instance, if you take a hyperbolic surface, a surface of genus at least 2, you take the unit cotangent bundle. Yeah, as we saw, then on this unit cotangent bundle, I have this contact form whose Reeb vector field is the geodesic flow, which defines a contact structure. So the geodesic flow in this case, since this surface is hyperbolic, happens to have a positive topological entropy. But moreover, you can show that any other contact form, which would define the same contact structure, would have a Reeb flow whose entropy is also positive. So the geodesic flow, being complicated enough, somehow forces any Reeb flow to be complicated in this case. Yeah, so for this contact structure, which I call psi-geodesic, you cannot find a contact form whose Reeb flow is integrable. Because if this was the case, then this would have 0 entropy, the flow, but this cannot happen. So there's an example. So that's the corollary is that this contact structure, this particular contact structure here, does not admit a Bott integrable Reeb flow, which means there's an obstruction. There's a contact topological obstruction. But again, if you go back to the same example that I had here, so where was it? Wait a second. We go back here. Yeah, so if you go back to this example, you go back here. Yeah, so now I have this is this geodetic contact structure, which doesn't admit an integrable Reeb flow, but there's this other contact structure coming from this pre-quantization construction, and this is obviously integrable. There's an obviously integrable Reeb flow. You see that you have one tight contact structure which cannot admit an integrable Reeb flow, and then there's another one which admits. So this kind of tells you that this question makes sense topologically, contact topologically. And then let me just tell you a couple of theorems. So for instance, in the case of S3, T3, and S1 times S2, these are all graph manifolds, very simple graph manifolds. All of the contact structures would admit an integrable Reeb flow. And then you can, and then we have work in progress, which actually tells you, supposed to, so, okay, let me tell you the conjecture. The conjecture is, given the graph manifold, every over-twisted contact structure would admit such a Reeb flow. So it seems like this over-twistedness doesn't give you any obstruction for the existence of such a thing, or in the dynamical terms, an over-twisted contact structure cannot force entropy. That's kind of the fancy way of saying what I'm trying to say. So maybe I should stop here, and then if you want to ask questions, then we can discuss further. Okay, thank you very much for your patience.
Right, thank you very much for the very entertaining, indeed, talk, Murat. And we are open for questions.
Yeah.
What is the definition of this entropy? Maybe you said it.
Oh, okay. Yeah, I thought this would be curious about it. So that's why I wrote it.
Does it
really
deserve
hard to
the name?
remember.
Is it just
Yeah. Sorry?
No, I'm sorry. To a physicist, of course.
Entropy sounds an alarm for a physicist.
Yeah, I know. I mean, it's in the dynamics. It's a very well kind of very. It's a notion which kind of nowadays takes a lot of attention. This topological entropy. I mean, it's not a new concept, but I can quickly tell you the definition. So what you do is basically more generally. Let's say you have a metric space, a compact metric space, and you have a continuous map. Yeah? And then you're looking at this discrete dynamical system. And then what you do is, let's say you fix an integer, and then you take 2 points, and then you look at the orbit of these 2 points up to time n-1. Yeah, and then you look at the distance of corresponding points, and then look at the maximal distance that you can see, And then this defines a number which you call dn of xy, and this defines another metric on the same space. Yeah, so now you're kind of defining for each integer n, so there's a number of iterates. The distance between 2 points is the following. You just iterate these 2 points n times, and then you look at the maximal distance between the corresponding iterates. And now this is your distance. This is your new distance between any 2 points. And then you say, okay, then you take some epsilon, positive, and then you look at the number of points, the maximal number of points that would be epsilon separated with respect to these distance. Meaning that it's like this. You start with a point, okay? You iterate up to n. Now you take another point, you iterate up to n, and then you check if the maximal distance is big enough. If it is big enough, if it is at least epsilon, then you put it in your bag. Now you have 2 points. Then you keep adding. And then the fact is that given epsilon n, this number is finite, this maximal number that you can get by just adding these points in your bag. And then you take this number, this is the maximal number of epsilon separated points with n iterations. And then you look at the exponential growth rate of this quantity. Yeah, so you take the log, you divide by n, now you send n to infinity, yeah, to make the iterates as much as big as you like. And then you get a limit, and then you just let epsilon go to 0 and see what happens. So this is like exponential growth rate of how orbits are getting separated in a compact space. Yeah, so this means that they are kind of things are binding around too much, so to say. I know it's hard to make sense of this definition. You know, maybe you always read something which kind of tells you that what this means, what it's yeah. This is what it is.
And what's the intuition why this should give 0 is everything is nice and integrable? And...
Okay, let me tell you. Well, first of all, it's actually not too. So if you just look, let's look at what happens in a regular level. So when you have this integrable system, you have a regular level, and around the regular level, so on each regular level, you have a tori, and then the Hamiltonian flow is a linear flow. But if you just think of T2 and then just think of a linear flow, I mean, you're not really getting separated. You know, this flow line stays parallel, and then they are not really going apart, so to say. Yeah, so it's even from the definition, for instance, it's easy to see if you have a linear flow on a torus, this quantity has to be 0. Yeah, for instance, this dn distance. Okay, let me tell you an easy explanation. So if your map is an isometry, for instance, this entropy is definitely 0, right? Because no matter how much you iterate, dn is your old d, and this number is independent of n, but you are dividing by n and taking the limit, then you get your 0. And in the case of this integrable systems, of course, you have this linear flows on the Lagrangian tori and their isometries. So it's like you're foliating your manifold with a Lagrangian tori, and then on each tori you have this, you know, that this entropy is 0, but then you have this variational principle for the entropy, in the sense that if you foliate your space, which like invariant objects, and then you look at the restricted flow and restricted system, and then if you get 0 entropy, somehow the total entropy will be also 0.
So in a sense, if the distances between originally adjacent objects don't grow exponentially, then
Exactly.
it should be 0.
Exactly. That's precisely what it is. Yeah. Yeah. So this is again, yeah. So as I said, this is kind of one of the measures for the complicatedness of your dynamical system. And then, yeah, so it's not really surprising to see that if you have an integrable flow, then the entropy you'll not really have a very complicated dynamics. But then again, the explanation that I gave was really about what is going on in a neighborhood of a regular level. So if the critical set is wild, you can actually get entropy. But then this Morse-Bott condition tells you that nothing wild is happening around the critical set. That's why you know that this entropy will vanish. But you could have let's say you could have Liouville integrable systems where you just ask the critical set to be of measure 0, and there you can really have examples where the entropy is positive. So this can happen. But then for us, it's really like this entropy somehow provides us some also. And in order to, for us, it's the motivation is not really dynamical. For us, it's really about seeing if there's any topological or contact topological obstruction for having simple dynamics, so to say. And there's also in this in our field, there's also nowadays this whole interest about being able to obtain complicated flows. And so the entropy forcing situation is very much studied. So somehow we are also in a way approaching to the question from the opposite side. Yeah, so okay, there are situations where the entropy is forced, like in this theorem. Yeah, so you have one contact manifold with a fixed contact structure, and here the entropy is forced. No matter what flow you take, the entropy has to be positive. When we were trying to figure out the complementary situation. So for instance, this theorem tells you that for these manifolds, contact topology does not force entropy. Yeah, this is another way of reading this result, so to say.
So maybe one other question. It may be trivial, but just to ask, if I think of the action, say the Reeb flow on the manifold, it's kind of a group action of R onto the manifold if you wish, and you are looking at its orbit. And a priori, is there a reason for this action to be somehow regular, that you can nicely classify the orbit into strata that
no, I mean,
regular orbits are kind
a priori
of...
there's no way. I mean, this is, I mean, so another kind of reason where these things, I guess, popped up was again is because of this classical question. So given a regular energy hypersurface, would you have a closed orbit of your Hamiltonian flow?
Yeah.
Yeah, this was an old question, and then this so-called the Weinstein conjecture for contact manifolds. So given a closed contact manifold, do you always have a closed Reeb orbit or not? So, for instance, in dimension 3, we know that this is true now. Yeah, and it wasn't really easy to prove this thing. I mean, there has been a big machinery. Some big machinery was invented. For the proof of this thing, and then in higher dimensions it's still open. So what is known in higher dimensions is, yeah, so for instance, even knowing the existence of a closed orbit, is a big issue. Yeah, so because maybe one reason. So for instance, I can say one thing. So for instance, if you have this Reeb flow, and then for some reason you have some Riemannian metric on your manifold, and then this Reeb flow is a flow by isometries. It's a killing field. Yeah.
Okay.
Yeah. So for instance, then in this case you can easily show. I mean, it's not that easy, but now it's classical that you always have closed orbits, because then what you can do is you have this R action. It's a subgroup of the isometry group.
Yeah.
Which is compact. So they take the closure. Closure gives you a torus. Yeah, and then you argue using the stabilizer.
So it's kind of for Riemannian manifold.
You don't have this geometric condition, this contactomorphism group. This is the place where this thing belongs. Yeah, this group is huge. Yes.
Yeah, I mean, when the action is what is called oh, come on, what was the name? I forgot the name. Proper. If then the action is proper, and we know that on a Riemannian manifold the action is proper, right? Which is, say, not the case for a Lorentzian manifold. If you have a Lorentzian metric instead, still isometries for the Reeb flow, you don't have the same conclusion, right?
Yeah, true. And then in the case of Lorentzian, of course, then one has to be a bit, I don't know, maybe
So there are compact Lorentzian manifolds.
Yeah, of
They're
course there
weird,
are,
but there are. So
yeah.
the Lorentzian is just kind of a reminiscent of it. May be any other thing. So generally speaking, if you don't know it's a proper action, then you don't know what the orbit structure is, right?
True. True. Yeah. That's one thing. And as you mentioned, the Lorentzian manifolds. Maybe I should say this. So another example of a contact manifold is, for instance, the space of light-like geodesics of a Lorentzian manifold. It's not that easy to see. Well, that's an observation by Penrose. So you take your Lorentzian manifold, and then you look at the space of unparametrized null geodesics, light rays. And this, I mean, of course, if it is Hausdorff, so you have some smooth structure on the space, but the space is not necessarily Hausdorff.
Geodesics emanating from the same point or everywhere?
Everywhere. Yeah, everywhere. Okay. So you can think it like this, right? So for instance, how do you, for instance, think of the space of, let's say, Riemannian geodesics? So you have the Riemannian manifold, and you have your kinetic energy Hamiltonian on the cotangent bundle, and then you take one regular level of, let's say, length 1, and then you mod out by the Hamiltonian flow. This is the space of geodesics, right? Space of unparametrized geodesics. So you take the orbit space of this R action. In general, this space is violent. But then what happens in the Lorentzian case also, so you have then your Lorentzian metric, which gives you your Hamiltonian. And then at each fiber, you have the boundary of your light cone. This is your 0 level, so to say. And then on this light cone, you have this Liouville vector field, which is like given by radial scaling is tangent. The Hamiltonian vector field is tangent. But then what happens is that they commute, and then you can look at the leaf space, and this is your space of unparametrized light-like geodesics. And then this has a local Euclidean structure, and then if this turns out to be Hausdorff, which is related somehow to the causality structure that you have, this becomes a nice manifold, and then it becomes a contact manifold, interestingly enough.
That's cool. It's hard to imagine, but sounds cool.
That is, yeah. I mean, so this, I think this was first observed by Penrose, and then his way of observing is really using Jacobi fields and stuff like this. It's really like it looks at the transverse sections of this light-like geodesics, and then out of this transverse sections, he cooks up this coordinates, this local Euclidean structure. But then with the Hamiltonian point of view, it is not that hard to imagine what is going on. Yeah, but again, coming back to the question, it's really like if you're able to put this R action given by the Reeb flow into a nice group, then you have some hope to be able to say something about the orbits and stuff. But in general, this lives in a very wild group. This contact morphism group is big, like the Hamiltonian, the space of a group of Hamiltonian diffeomorphisms, for instance, for a symplectic manifold is huge, right? So it's really hard to understand what it is. So so in that sense, a priori, it's a very non-trivial question. But then, at least now we know that in dimension 3, we know that there's always a closed orbit.
But you can't say how many such orbits there are, say.
There are now actually very strong statements. For instance, in dimension 3, you have this situation where either you have 2 or infinitely many. Then for instance, the 2, it's really easy to imagine the situation with 2. So if you take your S3, your round S3, and then you have this Liouville form, which gives you the contact form, the Reeb orbits are the Hawk fibers. Now you have infinitely many. So all orbits are closed. You have infinitely. But now what you do is you just take the Liouville vector field, but now you turn your round S3 into an ellipsoid in such a way that it's an irrational ellipsoid, so to say. And then what happens is that you get 2 closed orbits, and then any other orbit is dense. Now, this is the two situation. And then now we have a theorem which says that it's pretty much, I mean, there's one technical assumption, but people believe that it's just a technical assumption that you will always have two or infinitely many. But this is all in dimension 3, and then it requires lots of heavy machinery. It requires heavy holomorphic curve techniques, cyber-written invariants and stuff like that. I mean, it's really hard technology. And this only works in lower dimensions. So in higher dimensions, and then you this machinery has lots of technical problems. Yeah, yes, that's the situation.
Other questions?
I was wondering if you had any example in higher dimension. Of course, you wouldn't be able to draw some.
Yeah, I mean, the example in higher dimension, of course, I mean, so this example of the Hopf vibration here, like this example that we have on S3.
Hmm.
Yeah, so this happens in every odd dimension. Yeah, so you can put so here you can put S2n minus 1, and then you will get, let me see, 2. So S2n plus 1, then you will have CPn, and then you will have your circle vibration. It's the Hopf vibration again. Yeah, so your odd dimensional sphere, you see it as a unit sphere in Cn, or Cn plus 1, as you see this S3 in C2, for instance, and then you have this map from the sphere to the projective space. And then you have the circle vibration, and then in the whole thing applies. Yeah, so, or basically more generally, this pre-quantization picture, whenever you have a total space of a circle bundle or a principal circle bundle, where the base space is symplectic, and then the curvature is the symplectic form, then you have your integrable situation. And this also contains all odd dimensional spheres and many other things. But then, of course, in higher dimensions, having one non-trivial integral is not enough. You should have, let's say, in dimension 5, you should have 2. Yeah.
If you have a classification of the structures that do not satisfy the condition that you have.
Yeah. So, but this is I mean, this is tough. So this is the complementary. Trying to understand the complementary situation. So you want to understand if you have given the contact structure, whatever contact form you take to define it, whatever one form you choose, the resulting dynamics will be always complicated. So this is hard to show. But there are statements of the sort. Yeah. So this one in particular, this theorem, yeah, it tells you that on this contact-free manifold, there is one contact structure, such that no matter which contact form you take, the resulting rate flow will be complicated. And this you prove by saying, so you know that, for instance, the geodesic flow, so on this contact structure, there's one contact form which defines this. This is the Liouville form, whose rate vector field gives you the geodesic flow. And then since the surface has complicated topology, you know that the dynamics of the geodesic flow is complicated. And you can explicitly show that its entropy is positive, for instance. But then the question is, what about if I take any other contact form? Yeah, so a priori, there's no way to compare the dynamics, right? So at least with a trivial, like a straightforward way. For this comparison, you again need very high technology. So you have to sort of, the way that it works is like you create some sort of a homology theory which keeps track of closed orbits of a rate flow. And then you kind of, this homology theory, yeah, keeps track of the closed rate orbits, and then somehow is the invariant of the contact structure, which tells you that if you have one contact form where the closed orbits of the rate flow gives you, it's complicated enough. So you have enough. Somehow this is the connection that I didn't make really, but somehow, I mean, this entropy, for instance, you can also estimate this thing below by sort of the number of periodic points, so to say. If you look at the number of periodic points for a given period, if this number increases exponentially, so to say, as you increase the period, then this already tells you that the dynamics is complicated. Yeah. In the same way, you kind of argue that if you're one fixed dynamics, which is complicated enough, and then if you can compare this dynamics quantitatively to any other dynamics, that tells you that any other dynamics will be complicated enough, but this quantitative comparison requires very tough, very, very hard technique. Yeah. It's not easy. Yeah, so constructing the simple dynamics is rather easy than showing that you cannot construct one.
So in your definition, you based the integrability condition on this Morse-Bott functions, which restricts the form of the critical set, right? You say it's
Yeah.
not nice, right?
Yeah.
And then you spoke about the Liouville integrability, which says basically much less. It says, okay, let the critical point just be a null set according to whichever smooth volume form, right?
Yeah,
so
yeah.
that measure basically. I have the vague feeling that if you allow the integral to have such critical points like zero measure, then the problem would become trivial. It would always exist. Am I true?
You mean if you just, you mean if
Yeah, if
there
you-
would be like a topological abstraction for the existence of
Yeah.
such Liouville integral?
Yeah, my feeling is that there wouldn't, but I'm not sure. I don't have a good
I mean,
argument.
this would be something that I also would expect. But again, for instance, I mean, now I'm thinking how one can prove such a thing. So, yeah, then it would not be again easy. But somehow you want to argue that given any manifold, given a three manifold, maybe I cut it into pieces.
Mhm.
And somehow ensure that the pieces which has complicated topology.
And the point is you can
cover
add,
that part by some there my integral, maybe I'll define integral where the critical set will be just measure zero.
and that cutting into pieces, it doesn't have to be locally finite, right? Because you can have countably many little cuts and still end up with locally zero measure, although it won't be a submanifold anymore, but still zero measure. So it gives you an edge of doing kind of infinitely many cuts in a compact region.
Yeah. Yeah, I mean, yeah, it kind of makes sense. Yeah, but again, I mean, again, so that's kind of the thing. So you kind of want to show, so the claim here would be the following: given any three manifold, yeah, then I can. Now, by the way, this is something that I didn't say. Well, I mean, every three manifold is a contact manifold. This is one thing that I had to mention, but I didn't.
Sure.
Yeah. So there's any three manifold, any closed three manifold admits a contact form, admits a contact structure, right? So it's really like when you talk about three manifolds, this question really makes sense. Then you say, okay, given the three manifold, there's a contact form, there's a Reeb flow, which is integrable in the sense of Liouville. And then, I mean, the only way that I can imagine is really like, okay, you have to construct this object, right? So you have to construct your flow, and then you have to construct the integral. Then somehow you should be able to, so this complicated part, the complicated topology of this manifold, the places where you have the complicated topology, you should be able to recover in this way. But to be honest, I don't see any way of doing this, because you really need, I don't know, you need a construction to start with, Let's say I give you a hyperbolic three manifold. Yeah, so, okay, now on a hyperbolic question is then, is there a Reeb flow on this hyperbolic three manifold, which is integrable in the sense of Liouville? I don't know. I mean, I don't know how to construct it, I don't know.
Well, I mean, my vague intuition is that you begin with anyone which may not be integrable.
Yeah.
And then you look at the places, at the pieces where things go wrong. And in those passes, you just slightly modify it.
I see. But I mean, you see, I mean, again, you have to be able to start with something decent. So, for instance, in this case of this irrational ellipsoid.
Mhm.
So let's say you start with something. So you cannot start with something, for instance, with some rate flow. So you say I start with something and I modify. So if you think that you start with already has a dense orbit, I mean, any integral, for instance, that you have on this will be constant.
Yeah.
Yeah. So you have to start with something decent, I guess. Then you maybe modify it. But then the question is, what would be the decent thing? I mean, I would rather, I mean, if I was brave enough to try to prove such a thing, what I would do basically, then I would just try to localize somehow, I don't know. But I mean, in the case of a hyperbolic manifold, there's no way to localize the complicated topology. There's another problem. This is a global complication that you have. I don't know. Actually, I have no idea how one can attack this thing. Or maybe I don't understand what you are suggesting.
Well, I mean, if you don't have an argument at hand, probably I wouldn't.
No, I mean,
as I said, it's just a vague,
no.
it's kind of a vague intuition.
Yeah, I know. I understand what you're saying, but again, I don't really know any way of making this work, at least right away.
Yeah, there might be a trick which just doesn't come to mind immediately, but
yeah, could be.
might
Could
come
be,
if you think for it about it for long enough. Yeah. So
yeah.
if that is not the case, then let's thank our speaker once again, and let's conclude the formal part of today's seminar. Thank you, Dr. Saglam, for this very nice discussion.